In today's lesson we're going to look at the principle of conservation of energy. Generally in this course we'll look at particularly potential and kinetic energy. It's the most common one, but it can apply to other types of energy as well. So what do we mean by this? Well, if we look at a simple situation like this, when you drop a ball, to start with, the ball has gravitational potential energy, and we can work out, and then if we release the ball, it accelerates downwards and it loses that potential energy, but as we see, it's gaining velocity, it's gaining speed, and therefore it's gaining kinetic energy. And if we look at the values involved, now remember this software uses G as 10, so we're getting approximate answers here, but if we looked at it precisely we would still find the same conclusion. And we find that the potential energy that the ball had at the top was 8 joules. If you take this point to be 0, the actual light gate where you're measuring the speed. So it had 8 joules of energy above that, or it lost 8 joules as it fell through that. The kinetic energy can be worked out using their formula for that, Ek equals a half mv squared, and what we find is that these two values are exactly the same. Now, like I say, we are approximating here, but if you did it precisely you would find that they are still exactly the same. And so the loss of potential energy is equal to the gain in kinetic energy. And this is known as conservation of energy. We say the energy has been conserved. And what that means is that the total energy stays the same, but it can transfer between different types. Most examples we'll look at will just transfer from one type into another type. So, for example, when objects fall, energy is transferred from gravitational potential energy into kinetic, and as we'll see in a worked example in a wee second, that applies even when you're rolling down a hill, not necessarily when you're falling straight down. Now, one thing that's worth mentioning here is that the mass, if we looked at a heavier mass, a heavier ball, say the mass was 2 kilograms, then there you would get 16 joules. And what we'd find is that the speed is exactly the same, because when you put in the 2 kilograms into the Ek equals half mv squared formula, you would find once again Ek is 16 joules. And this reinforces the idea that we looked at the end of forces, is that dropped objects accelerate at the same rate, 9.8 meters per second squared, no matter what their mass is. So in this case you find the same final speed, no matter what the mass is as well. The mass is bigger than the mgh formula, then it will also be bigger than the half mv squared formula, and the value of v, if you were turning this formula around and working out what value of v you get, right, would be the same no matter what the mass is. So quite often the problems you can approach it from looking at energy or forces, and you get the same conclusion at the end of it. But let's look at that worked example I mentioned. So here we've got a ball of mass 0.5 kilograms and it's rolling down a slope, but the height of the slope from the top to bottom is 1.8 meters. And saying here you should assume all potential energy is converted into kinetic energy. Now we'll look next week at why that might not be the case. So potential energy at the top of the slope is mgh. So EP equals mgh, once again using G is 10, you get 9 joules. And that will be equal to the kinetic energy at the bottom of the slope as well. So Ek is a half mv squared. These two things are equal to each other. So a half times mv squared must equal 9. And now we can just do some simple rearranging, and you get v squared is 36, or v is 6 meters per second.